Hello, and welcome to EELE 367 Logic Design. My name is Brock Lemires, and I will be your instructor for this fully online summer course. The purpose of this video is to give you an orientation to the class so that when you're done with it, you'll be able to engage in the learning activities for the course. What I'd like to cover today is first give you an overview of the type of material that we're going to cover in this course, and then introduce myself because I'll be the voice and the hands that you see in the videos. Finally, what I'd like to do is go over the logistics of the course, so things like schedule and how you'll be graded, how you turn in assignments, and how you're going to perform the lab assignments. I'll also give you a walkthrough of the Brightspace Learning Management System so that you know kind of where to access all the materials. But most importantly, before we begin, if you are watching this, you need to make sure that you have the portable lab kit for this class. All of the laboratory exercises are going to be performed using this lab kit. And at this point, you should have either checked out a lab kit or provided me an address to ship you the lab kit. You are going to need this lab kit on day one. So it is critical that the first thing that you do is, if you don't have this kit, pause this video, email me, call me, or get in contact with me so I can get you this lab kit. Okay, so let's begin. This course is a continuation of EELE 261 Introduction to Logic Circuits, or an equivalent course. In this prior course, you should have gained experience with working with binary number systems, combinational logic design, and sequential logic design, and had an introduction to a hardware description language. This is the second part in this sequence of logic design courses where we go a little bit more higher in abstraction and only use a hardware description language in order to build larger digital systems. So what you should have coming into this class, whether you took 261 or an equivalent class, is the following. So in 261, we started with just looking at the basics of analog versus digital, where we learned that an analog system uses real information that is coded continuously, or that is continuous representation of the information, whereas digital is a coded representation. And the codes that we used were typically binary codes. So then we learned about the number systems. Okay, so we learned about instead of using decimal to represent information as a number, we learned the binary number system, and that was because computers are built with basically switches. Okay, so a switch can either be on or off, and that can produce two discrete voltage levels. And what we do is we use those voltage levels to represent a number, 1 or a 0. And then we combine those to create larger and larger numbers, which represents more complex information, and that's how information is acted upon within a computer. Within number systems, we looked at things like representing groups of ones and zeros using the hexadecimal number system. We looked at basic binary arithmetic, such as addition and subtraction. And then we looked at representing negative numbers using 2's complement. You should also remember Module 3, which was on digital circuitry and interfacing. This is where we looked at the basic logic operations, things like ands and ors and nands and nors and inverts, and we looked at their truth tables and how they produced an output based upon inputs, but it was all a logic value. And what we mean by logic value is that the inputs to a digital circuit are going to be either a 0 or a 1, and then the circuit is going to compute the output, which will also be a 0 and 1. So when we think about a logic gate, that's the basic operations that can take place on ones and zeros and produce an output. But we wanted to actually build hardware. So we needed to look at how do you create these basic gates in the real world. And so we actually looked at discrete parts from the 74HC series, and we were able to put these parts down on our breadboard and actually build basic logic circuits. Now, when we started building real circuits, we had to consider the real implementation of these circuits. So we had to consider things like power supplies and grounds. So these logic gates, they don't work unless you provide them a VCC voltage and also a ground. And we also needed to look at the interfacing between gates. So if one gate is going to produce a logic 1 and it's represented as a certain voltage level, the gate that receives that information has to be able to interpret that voltage level as the logic 1. So we needed to be able to design circuits that can interface with each other, and we needed to be able to understand the operation of these gates in order to interface them properly. So we needed to look at their data sheets. So we looked through their data sheets and we looked at a whole bunch of characteristics about these parts, and we also looked at both DC characteristics but also the AC characteristics, so how fast they switch. So once we had all these basic gates in hardware and knew how to interface them, we started looking at combinational logic design. So combinational logic design is where you build circuits that produce a logic output, and it's usually just one bit based upon multiple inputs, so 2 inputs or more, but they were more complex than a basic gate. So instead of an AND gate that had 2 inputs, you might build a circuit that could implement any arbitrary truth table, 3 input, 4 input, 5 input truth table, and we learned about how you actually synthesize the circuitry to produce the desired output. Within Module 4, we also looked at minimization. So we looked at how you can build a logic circuit to produce an output in many different forms. There are a variety of different topologies that you can use to produce the same output. So depending on what you're trying to do, you might want to choose one topology over another. So that was Module 4. So if you thinking back to Module 4, you think about things like the canonical sum of products, the canonical product of sums, a minimized sum of products using a Carnot map, or a minimized product of sums with using a Carnot map. And so that was what Module 4 was about. Then we turned our attention to the modern digital design flow, and we started looking at hardware description languages. And in the prior class that feeds into this class, we looked at Vhdl as the primary mechanism to design these digital systems. Vhdl is a language, and it gives us the ability to describe a logic circuit in a language. So we actually type out the functionality of the circuit, including the inputs and the outputs, how the logic is going to operate. And it was very powerful because it gave us the ability to simulate the result and make sure that the circuit is described properly before we actually build the circuit. Then the real power of the modern digital design flow is that once you have the Vhdl that's accurate, you can use an automated tool to actually synthesize the circuitry for you. And so we learned how to synthesize our Vhdl and create essentially a bit stream or a netlist that could be implemented on a programmable logic device. So we used an FPGA before in the prior class, and it was very powerful because we could immediately start building very large digital systems using Vhdl, and we allowed the tool to create the logic for us, and that allowed us to design at a higher level of abstraction. And then we moved on to Msi Logic, which is just looking at some basic combinational logic circuits, so things like encoders, decoders, multiplexers. And it was just to get a taste of, okay, there are combinational logic circuits that are so common, there's no need for everybody to design them. So what we'll do is we'll have them be designed for us, and then we'll just purchase them or use them. And we just looked at some common ones, but more importantly, we looked at how you could use the classical digital design approach to actually build them yourself. So if somebody said build a multiplexer, all you really need to know is how a multiplexer is supposed to work, create the truth table, and then synthesize the logic using a Carnot map. Or you could, if you knew how it worked, you could describe the multiplexer in Vhdl and synthesize it using an automated CAD tool. Finally, we wrapped up with sequential logic. This is where we started looking at circuits that could create their outputs based upon both the current value of the inputs and also the past values. So whenever you're talking about past values of something, you're implying that you need storage. So a sequential logic is circuitry that has some sort of storage mechanism. Storage is not, in this context, memory arrays, so things like DRAM in your computer. What we used was a D flip-flop. So a D flip-flop was a very fast storage device that could store 1 bit at a time, and it would only grab the input and store it upon a triggering event. And the triggering event that we used was the rising edge of a clock. So you should have all of that knowledge in your past, or you should at least know what I'm talking about roughly before taking this class. And so now we turn our attention to what is this class about? What is logic design about? Well, for this course, what we are going to do is we're going to continue using the same textbook, and really what we're going to do is in 261 we covered chapters 1 through 7. In this class we're going to cover chapters 8 through 13. This class is heavy in VHDL, so every lab is going to be done in VHDL. Almost all of the homeworks are going to be done in VHDL. All of the labs are going to use an FPGA board, and we're going to get to the point where everything will come together and we'll build a full computer system. So what to expect in this course, before we get into the individual content, is it is a fully online course. Okay, so you're going to be, instead of a lecture, you're going to be watching videos that I created for you. you're going to be doing homework in the form of either multiple choice quizzes within our Brightspace learning environment, or you're going to be doing VHDL simulations and uploading screenshots. You have the textbook, of course. Video and the textbook match exactly. So you can read if you prefer that, or you can watch videos if you prefer that, or you can do both to get kind of a different perspective. But keep in mind, I wrote the textbook and I did the videos, so it's kind of me describing the information in just two different modes. For the labs, you are only going to use the VHDL, and you're only going to use the FPGA and the analog discovery. So you don't need to use any discrete parts or your breadboard. You're just going to be doing a whole ton of VHDL. So that's where we are going. So let's take a look at the topics that we're going to cover. So we're covering chapters 8 through 13. What we're going to do is we're going to start off with what we call VHDL Part 2. So coming into this, you should have been able to create a very basic combinational logic circuit using VHDL. So you should understand things like what an entity is, what an architecture is. Do some simple signal assignments with some logical operators, so you can create a 3-input AND gate, or you can create a very simple sum of products form combinational logic circuit. Once we get to this class, what we want to start doing is looking at the rest of the functionality in VHDL. So this is where we're going to start looking at how do you model events that are triggered. Okay, so instead of being continuously assigned to the output like a combinational logic circuit, how do you create a D flip-flop, or how do you create a finite state machine? So we begin looking at more advanced techniques to model behavior, such as using a process and how to trigger the process and do sequential signal assignments. So the first module we cover is just looking at the rest of the functionality within VHDL so that you can model all of the types of digital logic circuits that we see in modern digital systems. The next module is where we just get some practice doing it. So we learn all the constructs of VHDL. Then what we do is let's just start looking at the most common circuits that you have. So we look at things like building a combinational logic circuit using an if-then statement or a case statement. How do you create a D flip-flop model? How do you create a finite state machine? How do you create a counter? How do you do register transfer level? So we look at the most common things that you need to design in digital logic, and we just do examples of it. Then what we do is we turn our attention to memory systems. So if you're going to build a computer someday, you need a large array of storage that's not a D flip-flop. Okay, so with D flip-flop is something we store information for, like a register or a finite state machine. But memory systems are different. Memory systems are where you have gigabytes of information that is stored in a different technology. So we need to, since we're going to have that logic functionality, we need to know how to model it in VHDL. So we look at some common technologies used to implement semiconductor memory systems. Then we look at the VHDL to model them. Then we get into programmable logic, just a short module that just looks at the common technologies that we use to implement some of these digital systems when we're prototyping, and sometimes just the final product. But we cover programmable logic because that's what we use in the lab. So we finally get to the point where we know enough about what we're trying to model that we're ready to look inside of the FPGA and figure out what they actually put on there. So once we look at this module, it's kind of neat because you actually, as you look at all the programmable little blocks inside of it, you'll understand what they do and how to actually build them. So then we finally wrap it up with looking at arithmetic circuits, and this is going to be more complex circuits, so things like adders and subtractors and multipliers and divides. And once we get through module 12, you get to the end and you will realize that you have put together all of the information needed in order to build a computer system. So you're going to be able to build the CPU of a computer system, the registers, the data routing in between it, the finite state machine that controls the execution of instructions. You're going to be able to build the memory system that can store read-only memory or read-only information. You're going to be able to model the memory that stores, volatile memory, so things like read-write memory. You're going to be able to model output registers. And we look at all of these different things that we've covered and you put them all together in the most common digital logic system that there is, which is a computer. So this course culminates with actually designing a complete 8-bit computer that is in VHDL. You're going to simulate it using a simulator. You're going to synthesize it using an automated CAD tool, and you're going to put the whole thing on an FPGA and run programs. So it's going to be kind of a culmination of the entire course. Before we get to the course logistics, let me give you a very brief background on myself, just because I'm going to be the person that you hear and see in the videos, and also I'm the person that wrote the textbook. So, and also I'm teaching the course, so sometimes it's good to know who is at the other end of this class. So, again, my name is Brock Ramirez. You can call me Brock. I've been a professor at Montana State University for 12 years now. I got my bachelor's degree from MSU back in '98. I then went to work as a hardware design engineer for Hewlett Packard in Colorado. And what I did there was I designed basically digital systems. They were acquisition systems for electronic test equipment, so logic analyzers. And so what I did was a lot of FPGA design work, a lot of printed circuit board design, a lot of just digital logic design. So I did this in my past life. And I worked for Hewlett Packard for 8 years while I chipped away at getting my master's and my PhD at the University of Colorado. So I got my PhD from the University of Colorado in 2005, and I ended up coming back to Montana State in 2006 and joined the faculty in the electrical and computer engineering department. So since coming back, what I've mainly focused my research interests in, or my research area, has been on digital systems. So, you know, digital systems are everywhere. But what I've been doing technically is I've been looking at creating reconfigurable computing systems, all FPGA based, to optimize the computer for a particular application. And what I've been doing is I've been doing a lot of work for NASA recently, where I've been building these space computers for various applications, and this has allowed me to kind of stay up to tune or up to date with what is actually being used in the real world. And also we've been doing some exciting things where students that work for me have been able to build, you know, real hardware that has been flown in space. So we have a computer right now as I speak that's on the International Space Station getting ready to be put into orbit. We just had a computer that was up there for a year where we tested how well it performed under bombardment by radiation. So this is the type of stuff that I do for my research. I also am the director of the Montana Engineering Education Research Center, and what we do there is we look at how can we improve engineering education. So, you know, engineering education it's a difficult thing, right? I mean, you have a whole bunch of knowledge that you have to bring together to perform engineering. So you need math, you need science, you need writing, you need communication, you need problem-solving skills. We put that all together and we form an engineer, okay? So it's not trivial, and it's becoming more and more complex because there's just so much more information available. The systems that we build are so complex that we just need to think about new ways to try to educate people. So I've been the director of that for 3 years now, and I've received numerous grants from the National Science Foundation to kind of conduct studies on how to improve engineering education, and I do a lot of it with MSU students. So that is me. Now let's take a look at the course logistics so you can actually get started on the class. Okay, so this online class is going to be administered through our Brightspace learning environment. Okay, so the address for this is ecat.montana.edu, and it'll redirect you a little bit to this ecat1, but anyway, just ecat.montana.edu. And you log into this using your NetID and password. And once you do that, if you have any problems with logging in, you're going to want to call this 994-3255 number, and they'll help you get in there. Once you log in, what you're going to see is all of your active courses. Now, before I actually go into our one of the classes, one thing I want to note is that 367 is actually being taught in different schedules this summer. So we actually have 4 different offerings of it. And so I'm going to kind of zoom in on this flyer that shows the different sections. So there's going to be a 4-week session that starts in May, 4 weeks that starts in June, another 4 week that starts in July. There's also a second 6-week session that goes from June to August. Then there's also a full 12-week session. Now, what I'm going to do is I'm going to poke into the first 4-week session. All the content is identical between the 5 sections. The dates are just going to be different in terms of when they're due and basically how fast you run the course. But I also wanted to point that out because if you're taking the class and something happens and you need to withdraw or it's just going too fast, you have other options. So if you're in the first 4-week session and something happens, you can go to the second or whatever, or you can slow down the pace a little bit and go to some of the longer ones. But I want to point that out because we're going to be looking at dates, and I want to make sure that you know, you know, that you're in the right spot. Okay, so I pop into here. I'm at 367, summer of 19. When you come into the course, you're going to be brought to the announcement screen, and I have an announcement here that just has the cover of the book and just says, okay, you're in the right spot. I'm never going to do announcements on D2L. What I'm going to do is I'm going to email you. So I'm going to email out reminders and announcements to your preferred email in my info. I'm not going to use the ECAT email system. You can set up your ECAT to forward. So if you happen to email my email within this ECAT system, it'll forward to my regular email. But you should definitely get your email set up so that your preferred email is what you want in my info. And that's because the email lists that I send to are going to be automatically generated, and they don't use your ECAT email, they use your preferred email. If you have any questions about that, if those terms don't make sense, just email me, then I'll help you get it taken care of. Okay, so here's what happens is you come into here, across the top of Brightspace, you see all the tools that you have, so quizzes, grades, assignments, etc. The way that I lay this course out, though, is everything is going to be linked within what I call the content area. I don't call it that. It's actually just what it's called. And I make these pages that basically have links to everything. So if I come down here and I go under course activities, you see there's a page for each of the modules we're going to cover, so 8 through 13. And then I put an additional page called course information that has contact information on it. And I link everything in here. So you should be able to get to every quiz or every handout on these pages. But just know that you can also access in multiple regions. So if you want to see your quizzes, you can click on quizzes up here, but everything should be linked within the page. So I recommend always going to the pages first. Okay, so we come in here, course information and syllabus. What you're going to see here is a link to the syllabus. This is going to be a big one because we're going to be looking at the schedule a lot, because this lists all the deadlines for you. Course overview video, obviously you found this. I do give you a review activity if you want. You can go in and take a look at some of the questions from the 261 prerequisite. So if you kind of forgot some of that stuff, you can actually go back and take this ungraded. You can do it as many times as you want. You can just flick through it. But then also there is some contact information in here. So myself, obviously, but we also have a teaching assistant, Coulter Barney, and his email is right here. We're both in Bozeman, and the preferred way to get a hold of us is email. All right, so I do have a phone, but email is preferred because honestly, I'm not in my office that much, but we all are both carrying around our cell phones. So if you email us, we can usually respond. I say within 24 hours, but realistically, it's going to be almost instantaneously because we're both going to respond. Sometimes we might just respond, hey, give me a minute to get back to my computer or something like that. But yeah, so email is the best way to do it. All right. On here is the required material list. So you're going to need a computer with running Windows. And the reason you need Windows is because we're going to be using software, Quartus, and you're probably familiar with that if you took 261, but Quartus does not run on a Mac, and there's just no way around it. So you have to either you just have to have Windows or have a Windows machine, because if you're running a Mac and you're going to try to like do the homeworks on some other computer, it's going to be really difficult. So just find a Windows machine to use and install the software on that. We're also going to be using a Analog Discovery 2, which has software. That software does run on a Mac, but it doesn't really matter because the majority of what we're going to do is using Quartus, and that only runs on Windows. Okay, you need the textbook, second edition here. If you have the first edition, that's fine. I have the second edition picture here. This really doesn't matter. At first edition, they're the same. I just have more homework problems in the second, and also the fixed typos. You need the portable logic lab kit. So this is going to have the FPGA and an Analog Discovery 2. You need that, like I said, right now. You need it on day one to do the first lab. And then you need a camera capable of taking short videos. So you're going to demo the lab by taking a 2 to 3 second video and uploading it to the assignment folder. And that's, usually just use your smartphone, and that's how you're going to do it. Okay, so I'm sitting here. I'm done. I've looked at this information. I'm going to go on to the first activity, which is Module 8. And so this is how the course is all laid out. So you have, you can see that these are the activities. We're going to come down here. A lot of this is going to be, you know, look at it. Read, watch a video, do the homework. Read, video, homework. Read, video, homework. Repeat forever until the course is done. Every once in a while, after you get through some of those, you're going to do a lab experiment. And the lab experiments are going to be, you're going to bust out your FPGA board and you're going to read through the description. I provide a video for the activity. Do it. And then there's deliverables. Sometimes they're videos of your demo. Sometimes they're a screenshot of your measurement, but you upload the deliverables to the assignment folder. And then at the end of each module, there's going to be an end of module quiz. Okay. And so that's how everything is laid out. And let's see. So let's look at these activities. We'll go through the syllabus and the deadlines last because we're covering kind of a lot of that now. Let's take a look at just a normal flow. You come in here, you read section 8.1 of the textbook, you watch the video, you click on it, it just comes to a YouTube channel. You can subscribe to my channel so that Digital Logic and Programming, so that you can get updates on other curricula that I post. Then you come down here, and the first homework is going to be a multiple choice quiz. So this one, you know, let me flip it into the view that you would see, preview. Homeworks are either going to be a multiple choice quiz administered through the Brightspace system, or a model sim simulation where you write VHDL and then you simulate it and then you upload screenshots of your waveforms and your source code. So this is an example of, okay, sensitivity list, how do you trigger a process? And thing to remember on this, the way the Brightspace is now is if you click on something, it'll save it right away. You can exit the quiz, come back later, but by the deadline, you have to make sure to submit it. Okay, so down here, you're going to see the submit button. You got to make sure to submit this thing so that it actually gets submitted. Once you submit it, it'll be automatically graded and you'll see your points right away. One thing to keep in mind when you do these, there may be multiple pages. So over to the left is kind of this navigation page or pane, I guess. It shows this one has one page with 5 questions. Sometimes there'll be like multiple pages. So you'll see page 2 has a couple questions, page 3, etc. So watch that. You don't want to accidentally forget a page. Okay, so that's how you do a multiple choice question quiz. And then let's come down here, section 8.2. Here's an example of you do some videos and now you're going to do a VHDL design simulation. So in this case, your homework is going to be to create a VHDL model, and I give you the instructions here of what you're supposed to do. Also what I do is I give you the test bench for this one, and I tell you what your deliverables are. So you're going to have model sim, and you're going to go ahead and simulate it. You're going to take a screenshot of the waveform, you're going to name it this, and you're going to upload everything to the assignment folder. So it'll upload your screenshot and then also your source code to the assignment folder. Okay, these ones need to be manually graded, so we'll wait until the deadline before we actually take a look at those. All right, so then you go back, here we go, video, homework. You're just marching along these activities, following the timeline in the syllabus. Now finally get to the first laboratory. You click on this laboratory description, and this is a big PDF. It's the same PDF that's used in 261, but let's go to lab 8.1 and take a look at this. So here comes your first lab assignment. You're going to notice I have this PDF with the description of it. I also have a video showing you kind of the overview of it, but I also show you kind of the deliverables. You have 2 deliverables on here, what they're worth. So first one is worth 90%, next one is worth 10%. And then I have some pictures. I usually give you a block diagram of the system you're trying to build. I usually show you what it's going to look like once you put it down on the FPGA board. And then as you work through, you're going to notice that when you're done with the specific part, on this one I walk you through setting it up in Quartus and all that sort of stuff. When you're done with a specific part, you're going to see red text, and that's going to give you some very specific information about what the deliverable is. So here I finally get done with this part and I say take a short video, less than 5 seconds, showing the preparation of your design. So that's the satisfies deliverable 1. Then we come over here, top.vhd, upload your VHDL file. That's deliverable number 2. So that's how all the labs are going to look. Okay, then you go back, do some more homework, another lab, and a module quiz, you're out. End of module quizzes are timed. So the difference between like a homework multiple choice thing and a end of module quiz is that the homework you can work on until the deadline. The quizzes, once you start them, you have a certain amount of time and then they expire. So you have to get them done. They're supposed to kind of emulate an in-class exam. Okay, so then you're done with module 8. Module 9 looks pretty similar. It's just read, video, homework, read, video, homework, lab, read, video, homework, read, video, homework, and you just march through the entire course activities and you get to module 13 and you actually are going to build a monster computer. So you're actually going to put everything together and you will, but it's the same thing. You're going to watch videos, you're going to have interim assignments, you're going to have demonstrations and simulations and everything. And once you got that project done, you're done with the thing. So that is the course activities. So now let me go back and let's talk about deadlines. And we're going to go over the syllabus, but we've kind of already gone over it. So let me look at the syllabus here. So now here we are. I'm looking at the first 4-week session, but everything is identical in all the other offerings of this course other than the dates. So we come down here, you got my name, contact information, Coulter's contact information, required materials, computer textbook, portable app kit, camera, prereq, website. We've already gone through this. Office hours, there's really no such thing as office hours because we're always here. It's an online course, just email anytime. Breakdown of your grades. So now you finally get to see what these activities are worth. We have 1,000 points possible. Homeworks are worth 150, labs are worth 450. Exam, end of module quizzes are 200, final projects are 200. So if you look at this, 450 points for your labs, 200 for the computer, that's 650 points. All the points and all the learning happens when you're doing these labs, when you're building circuits and actually testing them. So that's why it's weighted so much. Grading scale, we'll just go flat. So 90 and above is an A, 80 and above is a 80 to 89 is a B, 70 to 79 is a C. Academic policies, don't cheat. You can collaborate. The difference between collaborating and cheating is collaborating is you're working together with somebody else and you're both contributing, and it may end up resulting in you both have the same file, right? You both working on the same top.vhdl file. That's fine. Just make a note of it that you're both the authors on it, and it's fine. You each have to upload to your own account. That's collaboration. Cheating is where you just say, hey, give me your file and I'm going to upload it. And it becomes very obvious on our end when you upload somebody else's file because from the grading standpoint, they're triggered. We see when things are, duplicates, and so we have to look at them. So when we get triggered and we go look at it, if you can make a note that you worked with somebody, then we know that you're not turning in somebody else's work and it's actually a collaboration. Okay. Course components, we already talked about it. Read, watch a video, do homework. Every once in a while, you'll do a lab. At the end of a module, do a quiz, and you're going to do a final project. Here is now the big thing that you need to keep track of. This is the schedule. It tells you not only the activity, but what the point value is, and also when the deadline is. So the way that I do this is the deadlines are either going to be on a Wednesday or a Monday, and that gives you a little bit of flexibility. It's not like we're going to do something today, it's due at the end of the day. Tomorrow we'll do some more activities, it's due at the end of that day. What we do is instead, you kind of do a bunch of activities and they're due on a Wednesday. So in this situation, you'll notice, now remember this is the 4-week accelerated version that starts in May. You're going to do, a homework, then a lab, and then a homework. They're all due on Wednesday. Then you go on to the next part of the activities, and they're due the following Monday. Everything is due on noon, and so you're kind of getting this pattern of like when things are due. And this gives you a little bit of flexibility so that working on it every day is probably the best way to do it. But if you just get in a position where you're just like, well, I couldn't work on it today, I can put the hours in tomorrow, that does give you some flexibility. Okay, so then you go through all this and you notice that the lab points are worth way more than homework. Quizzes are worth a lot, but more than homework, but not as much as the labs. One big thing you'll notice is that like the multiple choice homeworks, they're not worth very much, okay? They're just kind of seeing if you remember something.
But the ones with an asterisk, those are VHDL simulations. Those are going to be worth a lot more. So those are the ones where you really show that you know what's going on. So you go through this entire sequence. All these different things have to be done in order to accumulate your grade, and you basically build up to 1,000 points. Hopefully everybody gets 100% in this class, and you are done. On some of the shorter courses, I do give you a suggested grid of how it might look. I don't do this for the 12-week course because it's kind of a huge grid. It doesn't make a lot of sense. But for some of the shorter courses, you can kind of look at like how I lay this out, where on a Monday you should be working on these assignments, on a Tuesday work on these assignments. They're all going to be due on Wednesday, okay? Thursday work on these, Friday work on these, and it's all due the following Monday. Then you start the next week, repeat. Monday, Tuesday, they're due on Wednesday. Thursday, Friday, they're due on the following Monday. So that's kind of the same information as is in this table, but it is laid out more like in a calendar fashion, okay? Now remember, across all 5 offerings of this course, all of this stuff is identical. The only thing that's different is the deadline, and the deadline just corresponds to how fast the class is. If you're doing a 12-week versus a 4-week, in the 4-week you are burning, okay? It's your full-time job and you can't take any other classes. 12 weeks, it's, slower. All right, the last thing I'll say is you have these objectives and outcomes. It shows you everything that you do is down to the section level with a specific learning outcome. So you don't just do stuff to kill time in a class, you do it for a reason. And the reason to do the activities, to learn something for 8.1 and to be assessed or do something that's graded, is to achieve a learning outcome. So that tells you what you should be able to do after you complete section 8.1. And I list all these out for you across every part, every chapter and every section of the book, so you know what you should be able to do. And so you should look at these every once in a while and go, can I do that? Did this prepare me? Okay. All right. So that is it. That is the course. We have gone through everything, logistics, background. At this point, you should have a lab kit sitting in front of you. You should be able to go right to module 8, and just start hammering it out. Read, watch a video, do homework, and you start building circuits on that FPGA board and running them. So good luck with everything. Don't stay stuck for long. Remember, you do have live instructors who are helping you throughout this summer. And if you're stuck for 5 hours and you can't do anything, you've been stuck too long. Don't stay stuck for a long period of time. If you're stuck, sometimes you just need somebody to see the problem from a different angle. So email me and Coulter, and we'll get back to you. Always email both of us at the same time, just so that the first one to get to it can respond as quick as possible. But good luck, and I look forward to working with you this summer.